Hi, I'm Martin Ducote.
And I'm Steve Summerlot. We're going to present our ME 872 final project, Thermoelastic Finite Element Code. Our program goals were to obtain transient thermoelastic solutions for a simple geometry, converge on a solution by mesh refinement, and then test our program on different loading and constraint cases. Now let's look at the geometry. We chose to use a 2D isotropic aluminum plate, 250 millimeters in length and 150 millimeters in height. To mesh the domain, we used HyperMesh, exported to a text file, which MATLAB could then read and plot. So to solve a thermoelastic problem, first we're starting with a heat conduction solution, because we're assuming our solution is semi-coupled, meaning the temperature field is uncoupled from the displacement field, but the displacement field is coupled to the temperature field. For this, we use a trapezoidal method and 4-node quadrilaterals with 1 degree of freedom per node. So our first 2D transient heat conduction case was constraining our domain on the left and right and adding a heat source to the top right. We're also keeping track of node 20 for our mesh refinement. So after refining our mesh 3 times from 15 elements to 960, we were able to converge on a 2D transient solution. So now let's look at this heat conduction. The elements in dark blue are at room temperature, and as the elements approach a dark red, they near 200 degrees Celsius.
Alright, now we're going to look at the 2D transient elasticity solution. From this, we're going to build off the heat conduction solution, build a new K, M, and F, and then use Newmark's method to solve the problem. So this is strain energy. As before, we've got total strain equals constants times stress plus thermal strain. But what do we do with the thermal strain term? We move our constants around, plug in, and this is now strain energy. The left side is going to give us our K matrix. The right is going to give us a thermal force term. So using strain energy and Gaussian integration, our final equation takes this form. So to test convergence, we're going to constrain the sides, add a force, follow node 3. So this is our y displacement, and you can see after 3 refinements, our mesh converges. This is an example of the solution. So now let's move on to results. How do we find stress contours? So we have displacements and temperature, but how do we connect it to stress? We're going to start with the strain displacement relationship, plug it into stress, expand everything out, and use our temperature solution to connect everything back around to stress. So now let's look at a few examples. We have the example from earlier. So this is our solution with the stress contours. Notice the stress concentrations. So here's case 2, the simple cantilevered beam. So these are our stress contours. We're plotting von Mises stresses. For our final case, we have 2 different loadings. Both receive force, but only the bottom one receives heat. Both solutions run for 100 seconds. The top solution, however, reaches equilibrium after 20 seconds. The bottom is still receiving heat, which is reflected in the stress lines. Thank you for your time and attention. Are there any questions?